All right, we're on to a new topic. Today, we'll be discussing multi-objective optimization. Up to this point, we've always assumed that there's one objective, but there are problems where it's of interest to have more than one, multiple objectives. So one must be careful when considering multiple objectives. I think it's perhaps a common beginner mistake to think of everything as an objective. That may come from a typical engineering process where we look at a set of requirements and say, these are the things we want to accomplish. And so we start to think of all of them as objectives. You know, I want this to be light, and I want it to be low cost, and I want it to be fast, and I want it to use less energy. We have to distinguish as best we can what things are truly an objective versus what things might be a constraint. Often things that are better posed as a constraint, meaning that there's some level after which we exceed or go below, let's say, it doesn't actually matter as much. It doesn't improve things anymore. An objective is something that if it keeps getting better or bigger, let's say minimization, keeps getting smaller and smaller and smaller, we would consider that better and better and better. Whereas many cases where, say, for example, we might say we want to minimize the loads on a structure or the stress in a structure, but really the stress is not an objective, right? Because at some point, once we reach a level where it's never going to break, or it's not going to break in, say, the lifetime of it, say, or 50 years, 100 years, couple hundred years, whatever it is, then going below that doesn't actually add any more value. So it shouldn't be, usually. We'll see some maybe reasons why you still might want to consider it, but generally that shouldn't be an objective. Another common reason to maybe use multiple objectives when maybe something better could be done is when we haven't reached an underlying objective. For example, we want to make this product that is efficient and is low weight or whatever, and maybe the underlying metric is something like a cost to produce or a profit that we expect to get, and sometimes maybe those are hard to capture, and that may be a valid reason why we can't do that. But we should be aware, right, that if we're doing a multi-objective problem, I guess on the one hand, sometimes we like to say that there's no such thing as a multi-objective problem, because at the end of the day, you're going to choose something. So even if we've got multiple things we're considering, there's some maybe balance we come to between those. And so how do we decide that? If we can formalize that, right, with maybe a higher objective, or by realizing that some of these are better posed as constraints, that's often ideal, as opposed to just treating everything as an objective. Having said that, there are many good reasons to do a multi-objective problem. I'm going to flip over to my slide so I can discuss. I can write some of those down. See, let me reset that, see if this will work. Okay, here we go. Connected. Okay, hold on. Sometimes this has some difficulty if I toggle this. All right, multi-objective optimization. So here are a few reasons why, and I should say when we think about multiple objectives, usually we are considering 2, 3, maybe 4, usually not many more than that. Becomes much, much harder to solve if we have, lots of them. So, usually it's around that many, maybe 5, but here are some reasons why we still like to pursue it, even if we're going to choose one design maybe at the end. One is to quantify the trade-off sensitivities. So there are cases occasionally where objectives are truly decoupled. They have no dependence, but that's not usually the case, right? There's usually some dependence in engineering problems, or just in life in general, right? If I have multiple objectives, multiple things I'm trying to do, even if I say they're in independent spheres of my life, putting more energy into one means I can't put as much time right into another. So they are still coupled, they're not truly independent. If they are, we can separate it, but usually there's some coupling. And that means that there are trade-offs. Meaning if I want to do better with objective A, I'm going to have to give up something with objective B. These are some fundamental trade-offs, but a multi-objective optimization can help me understand the sensitivity of those trade-offs, and we'll see that better. And we might say the slope, perhaps. We'll see this a little more clearly in a bit. Another reason is that sometimes we don't actually want to create one design, right? I mentioned that, you know, if we're going to have an objective that's going to lead to a design, but perhaps we actually would like to consider, sometimes we call it a family of designs or a portfolio of designs, multiple options. And some reasons for that might be is that we're not actually going to decide on design yet. For example, we may want to present to an executive committee, here are some options. And so we want to generate multiple solutions. Or it may be that we have a higher fidelity simulation tool that we're going to use later. And so optimizing with this lower fidelity tool to create one option may not be desirable. We may want to create a family of starting points. And another reason I kind of mentioned already is that the underlying objective may be too complex to formalize. And that may introduce more uncertainty than we're willing to take on. So as an example, say I'm designing an airplane and I have one objective that's going to be you know, my operating costs, let's say total operating costs, and another objective, which may be an environmental impact. And ideally, perhaps there's some underlying objective, right, that appropriately accounts for the costs of these environmental impacts on some long-term financial metric, but that may be really hard to quantify and really sensitive to all sorts of assumptions. So I may want to keep them separate and better try to just understand those trade-offs. Okay, so with that introduction, let's talk about how this works. First off, we're going to have to rethink our definition of optimality. So here's a picture of 3 designs, right, and I could draw a bunch more, but just to keep it simple, here's 3 designs and 2 objectives, F1 and F2, and I want to minimize both, right, because I have 2 objectives. So the question we'd ask ourselves, well, which of these designs is best? Well, if you think about it for a moment, it's very clear that B is not best, right? Because B is worse than A in both directions, right? It's bigger in F1 and it's bigger in A2. So A is better than B clearly, and in the multi-objective language, we say A dominates B. However, if we're comparing A and C, we cannot conclude that one is best. We might try to think of things like, well, A is closer to this one, this axis than this one, but and for a given problem, that may be a rational thing to do, or we might say, well, let's see which one's closer to the origin, for example. And as I said, for a given problem, maybe, you know, that could be rational, but in general, those are uncomparable, because remember, these objectives could be anything. They could be completely different units, and I could scale the problem any way I want, right? Just changing the scaling is going to move this, you know, shift the whole thing over. So where they are relative to the origin doesn't necessarily make sense unless these have the exact same units and they're scaled the same way. Then maybe, you know, we might consider that. But in general, the idea here is that these are non-comparable. We cannot say that one is better than the other. So to show that as a picture, well, I guess a common way to do this is to draw kind of this region of dominance. So remember, everything to the right and above A is worse. So anything in the shaded region we would say is dominated by A. If I was to draw one over by C, you know, it doesn't intersect B. So C doesn't dominate B, but if there's anything else here, it would dominate it. Extending that, let's say I had a bunch more points like this. So I've evaluated my function at a bunch of different places, and I'm plotting it against these 2 different objectives. And by the way, like I said, we can do more than 2, but 2 is certainly easiest to visualize. As we get higher, it becomes really hard to visualize. So if we were to draw these little boxes everywhere, I'd say, okay, everything here gets eliminated, is not optimal. These are eliminated. And we're going to end up with a set of things here at the edge, which are non-dominated. Each one of these red points is non-dominated. That doesn't mean it dominates everything in everything else, right? Like if I draw this one, it doesn't dominate everything, There are designs over here, for example, that are not dominated by this, but it means that nothing dominates it. There is nothing else here that is dominating these red designs. So really another way to think of it is if I drew kind of these shaded regions across all of these, I would get rid of all the blue ones, right? And I filled in all of those stuff. Okay, so I'm going to erase that. If we were to evaluate this to convergence, right? If we could evaluate everywhere, for example, an infinite number of points, then the set, and this is not converge, right? This is isn't, but if we went all the way down, right? This line would define the Pareto set. The set we refer to the x values, and Pareto front refers to the corresponding function values, although sometimes you'll hear those interchangeably. So you can call this the Pareto front, Pareto set, or whatever. So we've changed our definition of optimality to consider points that are now called Pareto optimal. So any point that's here now on this set is considered a Pareto optimal point. And again, everything that's on here is not better than one another, but they are the best. They're optimal from a Pareto set, Pareto sense. So again, Pareto optimal is the phrase we'd use. This is just another picture of that same idea. Let me show you an example of what I meant earlier when I talked about trade-off. So here is a Pareto front or Pareto set, Pareto front of let's say a wind farm. And I have two objectives. I'm trying to maximize my power. So I put it here with a minus sign so we can stick with minimization. But I also want to minimize noise. I want my farm to be quiet, right? I want to produce a lot of energy, but not disturb the neighbors. I could think about each of these objectives separately. So if all I cared about was maximizing power, I'd go all the way over to here. That would give me that point. All I cared about minimizing noise is I could get this design. And everything between here on this Pareto front gives me different options that trade off these competing objectives. Now, the shape of this curve can be really helpful because then I can, for example, start here and say, okay, here's the design I started with. I didn't care about the neighbors. I was just trying to maximize power. But now I'm trying to figure out how much do I have to give up if I want to reduce the noise. And that helps me maybe make some decisions. I could say, well, I can achieve this much noise with only giving up, say this much loss in power. And I can start to present some trade-offs that'll help us make decisions on whether this is worthwhile or not. The nature of this curve, right, can be very helpful. So let's say it was even flatter. Let's say the curve looked like this, for example, and continued on. Then we might say, wow, I can reduce the power by a negligible amount and reduce, or sorry, I can reduce, yeah, I did say, right, but let me say it the other way. I can reduce the noise by a lot, and I only have to give up a teeny amount of power. So that may be really worthwhile, and I wouldn't have known that if all I did was try to maximize the power. So this is a very useful purpose of multi-objective, one that is frequently used, is to try to understand these trade-off sensitivities, and then maybe go back and then, if we are going to choose a design at the end, then this can help us to, even if we say noise maybe is perhaps really a constraint, this sensitivity can help us understand what the appropriate constraint level is. And we'd say, well, we're going to accept, this type of level, for example, because that results in an acceptable trade-off. Okay, so let's talk about now some of the methods that we can use. The most well-known method is what's called the weighted sum method. This is used a lot, but it's actually not a very good method. It's the simplest, and we'll start with it because it's widely known and used, but there are better methods that are just as easy to use that we'll talk about. So those are generally preferable. But here's the idea, is that we're going to take these multiple objectives, and in order to put it into our optimization problem, we do need to have a single objective. So we're going to form it to a single objective and solve it multiple times. And the way we're going to do that is just by weighting the objectives. So we're going to say our new objective is going to be a sum of weights times our individual objectives. Right? And so this is going to be a sum over each objective. And often, although this isn't necessarily required, but we typically would choose the weight so that they sum to 1. Okay, so if I have 3 objectives, I'm going to choose 3 weights and run an optimization, and I'm going to vary the weights. And as I vary the weights, it's going to help me define that Pareto front. Let me make that a little bit clearer in 2 dimensions. So in 2 dimensions, in 2D, we can simplify how we write this a little bit. It's going to look like this. F of x equals W times F1 plus 1 minus W times F2. Right, so instead of defining 2 weights, we just took that second constraint that we wanted them both to be equal to 1 and just wrote it explicitly. And so here in this case, W is going to be a number between 0 and 1. Okay, so you can see, for example, that if I plugged in 0, this is gone, this becomes 1, so I'm just optimizing F2. And if I plugged in 1, this term is gone, and I'm just optimizing F1. So the numbers between 0 and 1 help me to generate points in between, right? So I'd have to solve a sequence of problems, or again, let's say, if I did just F0, maybe it gave me this point, for example, and maybe 1 just gave me this point, but then I choose other weights, and I'm going to get other points on the front, for example. Okay, so I solve a series of optimization problems. So this is the weighted sum approach. One way you could think about what it's doing here, and this will also help us see one of the limitations of the method, is that from this equation here, once I choose one weight, it gives me one value on the front. And we can show just by taking the derivative of df2, df1, if we go take the derivative, df2, df1, you can show that slope is just related here to the weight. So it's like once I pick a weight, I draw this line here, given by that slope, and I'm just going to push it and pretend like I drew that parallel. I'm going to push it down as far down to the left as possible. And as I do that, right, it's going to just hit my Pareto set like at this one point here. And then I'm going to pick a new weight, right? And I'm going to say, okay, let's just do something very different. And push it over, and I'm going to go until this is just barely tangent to the true Pareto set, and it give me another point. And I keep doing that for different weights, right? And of course, when I pick the 0s and 1s, that's going to give me the 2 ends here, slopes of an infinite slope and a 0 slope. Okay, so the benefit of this method is it's easy to conceptualize, it's easy to use. There are a few difficulties with this. One is that it's actually not obvious what values of W I should use to get me good spacing. Remember, so I drew these little points here, but I actually don't know what that curve looks like at all, right? Like I just get, if I do 0 and 1, I get these 2 points, but this curve could look like anything, right? It could be very steep in one direction. It could have, as we saw, like in the example I did, it could have these regions of concavity here. I don't know what it looks like. And so how do I choose W? Say, for example, it's really steep, then, that was bad drawing. Let me try that again. It might make sense, right? Just to say, well, let's just pick a uniform spacing in W. Let's just pick, you know, say I want 10 points, or I guess it'd be 11 if I did 0, 0.1, 0.2, 0.3, all the way to 1. But the problem with that is, you know, if I have even spacing here, then once I get here, I'm going to get 1 point here, and the next point may be all the way up here. And I don't actually resolve anything in between here. So I don't know very well how that behaves. So it's, you know, not the end of the world in 2D. We can kind of get some, or as I say, 2 objectives. We can run some points and kind of see we're under resolving and run it again. But it's, you know, in higher dimensions, that becomes really hard. When I say higher dimensions, I mean more objectives. Harder to visualize and harder to know what weights to choose. But another limitation of this method is that, as you may be able to tell from how I've described how this works, right? Or an equivalent way to think about it is that we're taking this curve and pushing it over. Anytime there's this non-convex region of a Pareto front, we can't get it. So that's shown here in this picture, right? If I took every line possible, every slope that I can, every weight I can possibly get, right, from 1 to 0, and all the ones in between, right? And I move them as far over as I can get this red portion and this red portion, but I won't get anything in here. Right, because this line here that I push down is just tangent to each of these. And if I tilt it any more this way or any more that way, it's just going to give me points over here and here. So because of the concavity changes, right, there's a concave portion here. I can't get it. I can only get this convex portion. So that can be a big weakness because this kind of behavior can happen on the Pareto front. All right, so a method that is, I would say, I would recommend over the weighted sum because it's really no harder to use and avoids much of that difficulty is the epsilon constraint method. So pictorially here, the idea is fairly simple. Here I'm just showing two objectives. Basically what we do is we, in the case of two, we just take one of the objectives and turn it into a constraint. Right? So it's going to be this inequality constraint. And so here I've got this infeasible region here, and I'm going to just minimize then the other objective. And so it's going to give me this point here, right? And then I change the constraint, I move it over, and I move it over, and move it over until I've swept out my Pareto front. As a more general way for more objectives, we could say we're going to minimize Fi, one of the objectives, subject to Fj is going to be less than or equal to epsilon j, and that's for all j that are not equal to I, right? So in other words, for all the other objectives, I have to add constraints, and then I can leave my other constraints as normal, right? I have inequality constraints, bound constraints, whatever. Those just go in the problem as normal. But with only two constraints, it's fairly straightforward. With multiple, I have to consider multiple combinations of the constraints. The advantage of this method is that I can now get this non-convex region, right? Because if I had a constraint here, right, I can still pick off these points. So I can pick off points all the way across the Pareto front. It's also generally more intuitive to select these weight or the values for epsilon because the weights were just some arbitrary thing that doesn't mean anything, right? Especially because these objectives could be totally different units, right? I'm trying to minimize drag, which is going to be in force, and I'm trying to minimize, I don't know, a efficiency, which is unitless. So when I try to combine them into an objective, or let's say cost and drag, the weight doesn't necessarily have any physical meaning. Whereas here, these epsilons, these do have a physical meaning, right? I'm actually constraining the objective, and I usually will have some sort of sense, or especially after I've figured out these are what are called the anchor points. Anchor. The anchor points are just the single objective optimum. If I just optimize each objective one at a time. So once I figured those out, I know the range, and so determining the constraints is usually more intuitive. So yeah, that's the basic idea. The main weakness of this method still is that even if I know kind of an epsilon range I want to do, if I space evenly in there, which is kind of the rational thing to do, I'm still won't necessarily get even spacing along the Pareto front, right? Because here, like in these regions where things are changing steeply again, I'm not going to get as much resolution as compared to areas where maybe it's flatter or whatever. I'm going to skip over big chunks of it. So I have to kind of go back and fill those in as well. Again, pretty easy, and with two objectives, a little bit more cumbersome with more. A method to improve on that is what's called the normal boundary intersection method. I'm not going to work through the details, just really the idea. I've written out a full algorithm in the book if you're interested, but I want to write out just explain kind of the idea. The main idea is that we first find these anchor points, and the whole purpose here is to try to get more uniform spacing. We first find these anchor points, and I'm drawing this with two objectives, but it's designed for any number, and especially is of course effective in those cases with more. And what we do is it's kind of like the epsilon constraint, but instead of searching along these vertical constraints, we're going to take and evenly space along this plane here. It's a line here in this two objective case. So these would be points that are evenly spaced. And as shown here, we're now going to do these constraints along directions perpendicular to that line. So for example, if I have these points that are evenly spaced here, I'm going to search along constraints along this direction, and that's going to give me these points along the Pareto front. And that's going to tend to give me a much more evenly spaced Pareto front without having to do a lot of extra iterations. So again, these type of methods really show their merit as you move into problems with more than 2 objectives, where it becomes harder to kind of see where to fill things in. Imagine you've got 5 objectives. Just visualizing that Pareto front alone is really difficult. You have to look at all sorts of slices, and you only see a teeny piece anyway. So you really want to have these methods that are going to be efficient at capturing it as best you can. For 2 objectives, which is probably one of the most common uses, if you're worried about the added complexity, and this still isn't too bad, but this is really simple. So there's rarely a good reason to use a weighted sum when this is, no more complex, but affords us many benefits. And this method, as we said, can be advantageous. A little more complicated. This is not, it's not quite the same. I mentioned this takes almost no additional work. This does take some more work, but it's not too bad. And it's especially helpful as you move up into higher numbers of objectives. Okay, lastly, I want to talk about a completely different method. So notice that all these approaches are really agnostic of the actual optimization approach that you use, right? So in all of them, I have to solve a sequence of optimization problems, either a bunch of different weights or a bunch of different epsilon constraints. And each one of those optimizations that I could use could be a gradient based, could be gradient free, could be whatever. But what we're going to talk about is a method based on evolutionary algorithms or genetic algorithms that with some adaptation can be used directly for multi-objective optimization. So the idea here is that if I'm running a genetic algorithm, remember that I have a population. I don't have a single point, I have a population. And I could, for example, let's say I plotted all the members of those population on 2 objectives. It might look something like this. And from that population here, I've now highlighted the non-dominated set. And as I keep that population, I could think about progressing that entire population down towards the Pareto front. So because I already have a population, this is actually a pretty good fit for this. And we do need to make some modifications based on our original genetic algorithm, our single objective genetic algorithm, but it's a fairly natural fit that we already have all these points anyway. So you could imagine that I started out and, maybe my initial points are like kind of way up here. It's really bad. But as the population improves, it moves further and further down, and I approach closer and closer to the true Pareto front. So let me describe the concepts of how this works. And I've written a full algorithm in the text if you're interested, but I will describe again the concepts. First thing we need to do is what's called a non-dominated sorting. So in the non-dominated sorting, what we're going to do is we're going to calculate what's called the rank of every member in the population. I've just drawn a few. So we don't need to know just the Pareto front. So I'll say it this way. First, these red ones, this is what we're used to looking at. That's the non-dominated set. We would call that rank 1. So these are the best. Now imagine I deleted all these red points and I figure out I figure out the non-dominated set again. That would give me these points in black. That's called rank 2. Now I delete those and I get the next non-dominated set. That's going to be, we call those points rank 3, and so on. We continue through, there's more than 4 ranks here. I'm just drawing the first 3, for example. So we have to run this non-dominated set algorithm, and that assigns every member in the population a rank. And again, rank 1 is the best. Rank 2 means they're dominated by rank 1 points. Rank 3 are dominated by rank 1 and rank 2, and so on. And I should say I'm describing a particular type of, there are many approaches to doing a multi-objective GA. I'm describing the basics of an algorithm called NSGA2, which is a widely known method. Okay, so that's rank. And the rank is going to help us decide which members to include in the new population. But the problem is not all members of a given rank are going to fit. So what's going to happen, I'll explain this again later, but what's going to happen is as I go to fill the new population, I'm going to, for example, put in all the rank 1 members and then all the rank 2 members. And then maybe I get to rank 3 and I can't actually fit all of rank 3. So I need another mechanism to sort the members in rank 3 to decide which of them to place in the new population. And the metric that is used is called the crowding distance. And basically the idea is that we want to get members that are separated, and this is going to help us preserve diversity. So with the ranking, we're getting members that are more fit. And with this ranking or this crowding distance, we're trying to get within a given fitness ones that preserve more spread. So the intuition there is that if I had a bunch of points that are really close, it doesn't really help to keep all of them, right? I want to keep maybe the ones on the edge and then other ones that are further. So basically what happens is we calculate these cuboids. It's called a cuboid because it's a cube, but in multiple dimensions potentially, which is a measure of how spread apart they are. And we kind of sum up the distance, the normalized sum of the distance of how much separation kind of surrounds my points compared to other points in the population. And those that are bigger, have more crowding distance, are more spread apart, we're going to favor because they are going to preserve more diversity. And I didn't draw it here, but the anchor points, the ones that are on the edges, we always give those a crowding distance of infinity. So we're for sure to include those ones on the edge. Okay, so to kind of just summarize the main algorithm, the reproduction and mutation phases or crossover and mutation are unchanged. Those all work the same. The selection process is a little different. So if we're doing a common approach is like what's called a, or in this NSGA is a crowding tournament. So we use the tournament approach that we discussed before. And in the tournament, right, remember what happens is that you randomly choose just 2 designs and you pit them against each other. And, one of them is going to go forth. What happens is that if we compare the 2, whichever one has a lower rank would go forward. And if they have the same rank, whichever one has a larger crowding distance is selected. Okay, so that's a minor change. That's pretty much all the same. So tournament, fairly similar, small change there. Reproduction, same. Mutation is all the same. The only difference is that at the end of the crossover reproduction phase, we don't eliminate the parents yet. We keep all the parents and all the children. So now we're going to have a population that's twice as big, right? So we have a population of 2n. So we've got, say, here's all the parents, and then there's going to be the offspring, child generation. And normally, right, I mean, there's some variations that decide between them, but often these are just gone and this becomes the new generation. But in this case, we're now going to consider all of them together. So now we have 2 to the n, and from this 2 to the n, we need to filter it down back to n, right? So we maintain the population. And the one reason to do this, I kind of briefly mention this with just the single objective genetic algorithm, is that we want to preserve what's called elitism. And that means that we're guaranteed that the best member of the population will survive. And that helps the convergence to go better. If we don't, so if it could happen, right, by that all the offspring, there's still a parent that's better than any of the offspring. And so we want to consider the entire population so that at least the best is guaranteed to always continue. Okay, so the way this works, the selection is that kind of as I described, is let's say this was the whole combined population, is that we first put everything in rank 1 and everything in rank 2 and everything in rank 3 and so on until we cannot fit a full rank anymore, right? So as I described, let's say I fit all of rank 1, all of rank 2, and then I get to rank 3 and it won't all fit. Okay, so everyone in rank 1 and rank 2 is going to survive, and then those ones in rank 3, I go back to the crowding distance and I sort them by crowding distance, and I put the ones that are more spread apart, have a bigger crowding distance, I put them in first. And then that defines the new population, and we move on to the next iteration. So as you can see, it requires a couple new functions, right, to do the non-dominated sorting and the crowding distance. But then we can reuse all the same mechanism of genetic algorithms that we already had, and it's can be effective for these multi-objective problems. I mean, the pros and cons as compared to the other approaches are more or less, assuming you're using a gradient base for the other approaches, are more or less the pros and cons of gradient base versus gradient free. Although we do get maybe a less of a penalty on the gradient free here, because we already have the population anyway, so there's not really a big additional cost to changing to multi-objective. I mean, there's a little more computation that goes on in the sorting and such, but we're already carrying around this population anyway, so it's kind of a nice fit. Whereas with the other cases, we do have to solve a sequence of optimization problems. Now, as the dimensionality of the problem gets bigger in X, not in F, but in X, like we have more design variables, it still may favor the gradient-based ones, even though there's many of them, just because the gradient-free won't scale as well. But for smaller dimensionality in terms of number of design variables, these evolutionary methods can be nice for multi-objective problems. Okay, so that's it. That's our quick coverage of multi-objective optimization. Next time, we're going to start talking about surrogate-based optimization.